Good morning, everyone. Thank you for giving me the opportunity to share with you some of the Nexus research activities that we have been working on for the last few years. I believe that it's timely, especially with all of the interlinkages that we see among the water, energy, food securities in Texas and globally. I'm Rabi Mohtar. I've recently joined A&M, and I'm really delighted to be here with you and share some of those experiences on the Nexus. What we will be talking about this morning is to look at an overview of some of the interlinkages that exist between water, energy, and food, and more particularly, we'll zoom in into some of the challenges that we face here in Texas, making some references and links to some of the global security allocations and natural resources allocation around the globe. We would bring some of the to the forefront, some of the interlinkages that exist between these resources and the need for us to look at a system that integrates the trade-offs among the water, food, and energy, and look at an integrated system of the Nexus. And I'll share some of the ongoing activities when it comes to modeling and projections of these. And I'm hopeful that out of this very short intervention, there will be some key questions raised and maybe some directions in which we as a A&M community, especially in the College of Agriculture and Life Sciences, we would be taking on as an integrated approach to resource allocation. Let me start with a global picture. And even though, as much as I'd like to tone this danger down, it's really a head-on crash in many, many ways. Years ago, water security used to be a localized issue for some nations. And I do believe that with the globalization over the last several years and with the widespread shortages in water and in food, water and food and energy security are rising to be major global threat to not only to our societies but to our economies. And I do believe that there is a head-on crash unless we look at ways in which we look at trade-offs in water policy to the other resources and vice versa. And I think these interlinkages are becoming more and more acute because of our interconnectedness with the global economy. So I gave here some examples of this interconnectedness and some of these security issues. We have to come up with 40% additional water in the next 30 years with the business as usual scenario. The majority of this would be going into partitioned. I would say over 2/3 of that traditionally has gone to agriculture production. About 30%, 20 to 30% has gone to energy production, because most public do know that it does take water to produce food, but many of us do not realize that it does take water also to produce energy, and vice versa. It does take energy for our current agriculture production, which is energy intensive. So the same picture gets gloomier when we look at additional 40% by 2030 of additional energy demand. This, of course, varies by nation, and the need for additional water to satisfy that demand, and also our inability as far as the infrastructure that we have for the energy system to supply that increase in the energy demand. And depending on what resource you use, it's between 50% to doubling the food supply. And a lot of that is alarming because of the water footprint and the energy footprint that this brings along. I think the recent figure that came out of the Feed the Future report that came out of the White House suggests 75% additional food production that we need. In addition to the water footprint, the question is, do we have additional or do we have sufficient land to produce that much food? So it really put a puzzle in a mathematical term is an ill-defined problem. There's no solution to it unless really we get out of our box and look at the win-win situations and the interlinkages between all of these resources. I may not have the recent statistics here, but the recent report that was issued earlier last month from the IPCC the picture doesn't look even that it looks even worse than what you have seen here. So the point I'm trying to raise is that there are resource scarcity issues when it comes to food security, water security, and energy security. The other major point is that globally these resources are interconnected and must be looked at as a bundle as compared to a silo approach that we have been using in the past. If we look at, focus our attention for the next few minutes on Texas, we've all have seen the growth and the projected growth of the state. Many cities, the major cities, in fact, if you look at the recent population growth and census report, the top 5 cities in the country that has the highest growth rate, many of them, I don't want to misquote here, but at least 2 or 3 of them are from Texas, which signifies the important economic growth for the state. But that comes also along with other challenges in terms of the resources. Another snapshot is our dependency on fracking as we move into the future. And we know the technology has been led by Texas, and Texas has led the country in terms of the energy independence. That, however, comes with some concerns in terms of the water usage and some of the environmental issues that must be looked at. And as we look at more and more of our energy demand supplied by shale gas, we ought to look at the other dimensions in terms of the water footprint as well as the environmental concerns. If I look at the water demand, and if you recall that 40% gap in the global water gap, the picture doesn't look any better when it comes to Texas. There is about 35 to 40% water gap in Texas. If we look at the total water demand, that is in the red line, as compared to the water supply, which is the white or gray line, that gap has to be met in the next 30, 40 years. And if you look at all the water demand sectors, namely the food, which is predominantly the major of those sectors, and the projection of the water that is used in domestic. The reason that is growing because of our urban city and urban development and the urban growth that we are experiencing and we will be experiencing. So the picture doesn't look any better when it comes to Texas as far as the water gap is concerned, and this is the projected deficit that we'll be looking at in the next 30, 40 years of 8.24 billion cubic meter of water that we need to find. And I call this the new water. That has to come either from doing a better job at the efficiency and the water use that we have, or we have to come up with what I call new water, and I'll describe that shortly. So if we look at the deficit, the projection of where that water is going to come from will be a combination of various strategies. One of those, the main source, is going to continue to be conventional water sources, and that's the way we know it in terms of surface and groundwater, and a lot of that is renewable. However, there will be other we have to really work hard at conservation. Now, that conservation is a general term. A lot of it would be probably in the agriculture sector, but I'll bring in later a new opportunities for us to look at reuse of water and recycling of that water, and how can that be helpful in meeting the agriculture water demand. If you look at the non-conventional water, and that's the water coming in either from desalination or from reuse, that can constitute up to 16% of the future water demand. So the projection over the next 30, 40 years, there will be 2.24 million cubic meter of water needed to generate electricity. That's a huge growth in terms of the water for energy dimension that we also must be looking at. So if I take a kind of a overview look at the interconnectedness of these resources, all of the new water, and I'm calling new water, is that water that is generated, is the produced water, whether it's coming in from a recycling. In fact, there was, driving here from Blackland, there was a program about some new cities in I forgot the name of the city, but it's one of the first in the country, a Texas city that's looking at a mix of 50-50 of its water coming in from a lake mixed with a pure wastewater that has gone through several treatment. That 50% of the water supply for that specific city is what we call new water. There are other sources of that new water, but collectively they constitute up to 16%, and that could 16% of the water deficit. So the question is, can we get more? And of course we can get more, and there are a lot of research that we need to be digging into our either trying to start with a clean slate into our current practices, whether it's agriculture, whether it's in the oil, or whether it's in the municipal, to start looking at ways to conserve and creating new opportunities for us to bridge that 40% gap. In specific here, I'd like to highlight the green water space, and this is traditionally has been known as dryland agriculture, and with the intensification and with the pressure to produce more out of a piece of land, we have lost that concept of green water management, which I think we need to probably revisit that and look at water productivity concepts as compared to land productivity. So changing the parameters of the system may allow us to have a fresh look at the green water management opportunities that may be out there. Now, some of the research topics that we need to look at is the long-term impact on soil quality of using non-conventional water on soil quality, on health, and that is over the long term, and the feasibility of using some of that water for electricity production, but also for the energy sector in general. The consequences of those are unknown and need to be looked at. If I look within the state, 14 out of 16 regional water planning groups recommend water reuse. And the question is how much and where to start. And I gave an example earlier. I apologize, I didn't recall the name of the city in Texas, but there are already some regions that are water scarce are looking at creative ways of meeting that water gap. I'd like to, and then the last bullet is something that is the gap by 2060, water needed to generate electricity, and some of it could be coming in from the reclaimed recycled water. So going back to that ill-defined problem with the puzzle and new ways of doing business, I'd like to maybe explore that nexus as a holistic, integrated view of looking at the whole system and identify key hotspots that we can move and mobilize and drive our efficiency, not only for water, but also for food and energy as well. So if I look at this conceptual framework and identification of, at least initially, identification of all the interlinkages, but not only stop at the identification, look beyond at the quantification of these linkages and look at where would investment in terms of research and policy could be made. And in specific, I'd like to introduce the Nexus tool that we've been working on that exactly does that. It looks at exhaustive list of relationships and interrelationship between these major resources and try to capture that within a modeling framework, not necessarily only to simulate, but also to project and look at trade-offs for a certain policy. So when all of the interlinkages are defined and are integrated within a common platform, we start looking at what if scenario and allow us to look at, for example, if you want to push a certain water technology, desalination as an example, what would be the trade-off of the desalinized water on carbon emission, on energy use, on land use, because some of these, desalination happen not to have a land footprint. But if you look at technology such as solar, it does require a land footprint. And there hasn't been an integrated view, simulation type activity that does take into account all of these. So the simulator, which we call Nexus tool, takes all of these relationships, put them in a platform in which you as a user, and the user could be a policymaker, could be a scientist, could be somebody who's really looking at those trade-offs, that enters a certain parameters for the scenario or for the certain policy that they want to test. And the tool gathers that information and allows to rank certain scenarios as far as their sustainability. The one thing that I'd like to pinpoint out here is the role of the policy. And I call it here a policy, but it's really a platform where a user, most likely that person could be in a position to make an action, to induce an action, would rank all of the output. The output of this could be water footprint, energy footprint, carbon emission, environmental indicators. There's a bunch of those output. As a user, you have the chance or the choice to rank these based on what is important to you. Is it the cost that's driving your decision making, or is it the environmental concern, or is it the water usage or the energy usage? So you have the chance to look at an assessment and ranking of these, so you can rank your scenario and pick the scenario that, according to your own constraint, your own parameters, or your own selection of this ranking, what would be the most sustainable scenario. And I think this is not a solution for all, but this is at least a platform that we've been working on to help guide two things, to help guide policymakers in terms of selecting a certain sustainable practice, but more so as a scientific community, it helps us identify the hotspots in which we can invest more energy, more research, more resources to work on, rather than have a kind of a snapshot, random shot at where we would invest our energy and resources. I apologize, I won't be here with you to take questions, but I do look forward to engaging with all of you further as we move forward in this discussion. And thank you for the opportunity, and thank you for listening.